Welcome back. Let's do some more examples of Lewis structures. So this time, let's do this one. So last time I mentioned that SO3 is not sulfite, that is sulfur trioxide. This time, we're going to draw a Lewis structure for the sulfite ion. Think about what that charge means in terms of the number of electrons it has, and think about what we do when we're counting valence electrons when we have a negative ion. So go ahead and pause the video, draw that Lewis structure now. So here is the Lewis structure for the sulfite ion. Let's go ahead and do some more examples. Draw a Lewis structure for BeCl2. Go ahead and pause the video and do that now, please. Beryllium is one of the exceptions to the octet rule. It is stable with 4 valence electrons, which it can achieve by forming 2 covalent bonds. So there is the correct Lewis structure for that molecule. Let's try another one. Draw a Lewis structure for C2H6. This one we'll do together. A little bit different. We have a hydrocarbon. There is really no central atom here, so just show the carbons bonded to each other. Follow the same steps. Make sure to add up the valence electrons, and then distribute the hydrogens as best you can to each of the carbons. So right now, each carbon has 2 electrons and needs 6 more. And it just so happens that we have 6 hydrogens that we can distribute, 3 to each carbon. So there's a Lewis structure for C2H6. All right, let's try another regular one. Draw the Lewis structure for xenon tetrafluoride. No, this is not a trick. Yes, xenon is a noble gas. Some of the heavier noble gases can form compounds, and xenon is one of those. And so go ahead and draw the Lewis structure for this molecule. Pause the video now, please. The Lewis structure for xenon tetrafluoride, we can see that xenon exceeds the octet rule, which there's no choice here. We have those 4 extra electrons. They need to go on the central atom. All right, next one, go ahead and draw the Lewis structure for iodine trichloride. Go ahead and pause the video and do that now. Right, there's the Lewis structure for iodine trichloride. Again, just like in the last example, we see that the central atom exceeds the octet rule. Again, we have no choice here. So again, if your Lewis structure doesn't look exactly like this, that's fine. There's a reason why I drew it this way. And so we'll talk about that later. All right, one more. Draw a Lewis structure for sulfur dioxide. Go ahead and pause the video and do that now. So this one's interesting. We have a double bond, and if you put the double bond on the left side, that's fine. We'll talk about that situation later as well. And we have a lone pair of electrons on the central atom. So remember, always check to make sure that each atom in the molecule or polyatomic ion satisfies the octet rule. If the central atom doesn't satisfy the octet rule, we need to make double or triple bonds as needed. Up, we have molecular geometries, which describes the 3-dimensional shape that a molecule or polyatomic ion takes. And so hopefully you had a chance to memorize the molecular and electron geometries. So molecular geometries are only for molecules and polyatomic ions, so you may want to add that to your notes. The shape that a molecule takes is based on the VSEPR theory, valence shell electron pair repulsion theory, which states the geometric arrangement of atoms around the central atom is determined solely by the repulsions among electron pairs. And it doesn't matter if those are bonding pairs of electrons or lone pairs of electrons. Repulsions among electron pairs in the valence shell of the central atom. Electron pairs take positions such that repulsions between them are at a minimum, meaning that the electron pairs are going to arrange themselves around the central atom as far away from each other as possible. So if you take a look on pages 326, 327, we have some ball and stick models there trying to kind of show you 3-dimensionally what the different molecules look like. So here are the symbols we're going to use, generic symbols for describing molecular geometries of different types of molecules. The symbol we'll use for the central atom is A. Bonded atoms can be B or X. I don't remember what your flashcards say, so either way, B or X. And then for the lone pairs of electrons on the central atom, we're going to use E. All right, so let's take a look at our first one, which is linear. I'm going to write a couple things. Linear is AX2. Looks like this. So you have the central atom and two atoms bonded to the central atom. So these electron groups here, the furthest they can get away from each other in degrees is 180 degrees. So the distance between electron pairs, 180, or we call this the bond angle, is 180 degrees for a linear molecule. Next up, we have trigonal planar. So that's pronounced trigonal, which is AX3. So we have central atom and three atoms bonded to the central atom. The furthest away that those electron pairs can get from each other is 120 degrees. There's one derivative, it's called, of the trigonal planar geometry. So a molecule or polyatomic ion that has a trigonal planar electron geometry, but because not all of the electron groups around the central atom are bonding pairs of electrons, we call it a derivative. And so the one derivative is this. So this time we have still three electron groups on the central atom, except this time we have two bonds and one lone pair. And the name of this shape is bent. So three electron groups, 1, 2, 3. So trigonal planar electron geometry. But because we have one lone pair of electrons, the molecular geometry is called bent. Next we have tetrahedral. Generic formula AX4. Looks something like this. Now we're showing this two-dimensionally. It looks like the furthest that those electron groups can get from each other is 90 degrees. You got to think three-dimensionally. In 3 dimensions, those electron groups can orient themselves further apart from each other than 90 degrees. So the bond angle is 109.5. All right, there are two derivatives this time for the tetrahedral electron geometry. One of them is this, AX3E. Looks like this. You have 4 electron groups. This time we have 3 bonds and 1 lone pair. And the name of this is Trigonal Pyramidal. So be careful with trigonal planar versus trigonal pyramidal. AX3E, Trigonal Pyramidal. Another derivative of the tetrahedral electron geometry. Whoops, kind of hard to see there. AX2E2. Again, we have 4 electron groups on the central atom. We have 2 bonds and 2 lone pairs. And the molecular geometry is called bent. So notice AX2E is bent, as well as AX2E2, also bent. All right, trigonal bipyramidal is next. AX5, central atom and 5 atoms bonded to the central atom. Try to look in the book and see the arrangement of these electron groups around the central atom. So try to think three-dimensionally. We have 3 electron groups that go around the equator. Those are the equatorial positions. The distance between these equatorial positions is 120 degrees. And then you have a bond sticking up and a bond sticking down, if you will, perpendicular to the plane of the other bonds. And these are called axial positions. So you have axial, A-X-I-A-L, and equatorial. So distance between axial and equatorial is 90 degrees. All right, for this one, we have 3 derivatives. Hopefully you're seeing a pattern here with how we come up with those derivatives. First one is AX4E. Looks like this. So the lone pair of electrons occupies one of the, actually I'm going to make this similar to the last one. Let me fix this. So the lone pair of electrons occupies one of the equatorial positions. So AX4E has a trigonal bipyramidal electron geometry, and the molecular geometry is known as seesaw. So I hope that's in your book. Your book actually calls it irregular tetrahedron. I prefer seesaw. Another derivative, AX3E2, looks like this. Let's see if I have some room for that. This time we have the lone pairs of electrons that occupy two of the equatorial positions. So I'm going to put those there. AX3E2, this is called T-shaped, and you can see why it is called T-shaped. And then we have one more, AX2E3, and I'm going to see if I can draw that here. This time all three lone pairs of electrons on the central atom will occupy the equatorial positions. And so we get something like that. And the molecular geometry is called linear. All right, one more. Octahedral does not mean AX8, but rather AX6. If you look in the book at the octahedral, if you connected all the bonded atoms to each other, you'd have a shape that has 8 sides, or an octahedron. So it looks like this. Like trigonal bipyramidal, we have this time though 4 equatorial positions, 4 bonds or 4 electron groups around the equator, and then the 2 axial positions. Distance between all 4 equatorial, and distance between axial and equatorial this time, all 90 degrees. All right, couple derivatives. AX5E looks like this. I'll draw it over here this time. So lone pair of electrons on the, I did it on the bottom axial position. This is known as square pyramid or square pyramidal. Your book calls it square pyramidal. I'm fine with square pyramid. Looks like a pyramid with a square base. One more, we have AX4E2. Again, still 6 electron groups on the central atom. This time I'm going to put those lone pairs of electrons on the 2 axial positions. And so we get something like that. This one is called square planar. So be careful, like trigonal planar versus square planar, trigonal, pyramidal, square pyramidal, all these weird names. So those are all the different types of electron and molecular geometries. So now let's go back to our Lewis structures, and we'll give the molecular geometry. We can do both if you want, but primarily we're focused on the molecular geometry for each of the molecules. This section, either we will do this together in class or I will post another video since I am out of time here. All right, thanks for watching.